So what are the implications of 1 + 1 = 2? First of all, two non-parallel lines in a plane meet at a single point. That's because codimension 1 plus codimension 1 equals codimension 2. You fix one line, it takes away 1 degree of freedom. Fix the other line, it takes away the 2nd degree of freedom, and it limits you to a single point. There's an analog of this that applies if you replace straight lines with curved functions. So if this red function is higher on the left, and the green function is higher on the right, then there must be some point where the two intersect. Okay, this is sometimes called the intermediate valued theorem applied to the difference of these two functions. You can think of, if you think of one of these axes as time, and these is like charting, maybe you have a single one-dimensional road, and this is telling you where the cars are on the road at a given time. This is telling you that cars can't pass each other without having to intersect at some point. So if a car is behind, if the red car is behind the green car at the beginning and then it's ahead of the green car at the end, there must have been a time when they were at the same place. There's a more sophisticated version of this called the Jordan curve theorem, which says if you take any self-intersecting loop, red, that it always divides the plane into an inside and an outside, and any green path from the inside to the outside must intersect the red curve. Now, if you were to look at this picture in time, you would see as you move time, occasionally there will be times where the vertical line, or fixed time, would intersect like 2 points. So you start here, it would intersect 0, then you'd have 2 points that sort of appear from nowhere. They come apart, and then later they would come back together. It's kind of a slightly more complicated thing. There could be times with a bad curve where you have many different points, and then they merge together. But essentially, it's a version of this theorem we have here. There are other versions of this. Double crossings. How many of you have played the game of hex or heard of the game of hex? Like maybe 20% of you. So this was marketed by Parker Brothers. The game, here's a large version of it, where basically you take hexagons, you put black on 2 sides, white on 2 sides, and we take turns putting on hexagons of our color. And black is trying to make a crossing from black to black, and white is trying to make a crossing from white to white. Okay, but it's an interesting theorem with this game that you never get stuck. If you keep playing until the game's end, there always will be one player who wins at the end. Another way to think of that is if I tile these things randomly, or take any way of putting a coloring of these things, black or white, let's just do that randomly. So I just colored these things black and white at random, then there will always be either a way to get from black to black, or a way to get from white to white from these 2 sides. If there's a black way, that blocks there being a white way. If there's a white crossing, that blocks there being a black crossing. These little dots are places that are called pivotal, meaning if I change the color of this dot from black to white, that would change everything and make it so I could get in a white curve all the way from one side to another. But you can also see that if these hexagons are colored randomly, just by symmetry, both of the 2 possible outcomes have to have probability 1/2. So that kind of tells you something interesting. Either you cross from one side to the other in black, or this way in white. Both of those events are equally likely. So it suggests crossing events like this should have some non-trivial limit, maybe, as I take finer and finer grids and always use fair coins. And there is something called Cardy's formula and Smirnov who proved this, that really gave us a really precise sense of what happens in the limit as you get finer and finer hexagons. What are the probabilities of crossings for different kinds of even non-symmetric regions? But just this simple argument I gave you here gives you the first glimpse of the idea that there should be a continuum theory. The same holds, by the way, if the colors are chosen from something called a 2D Ising model. If you know it, don't worry. You'd be glad. If you don't know it, don't worry. It's like a toy model of magnetism. We can similarly consider bond percolation, where every edge of a square grid is randomly declared open or closed per a fair coin toss. So here's the way I imagine that. So imagine you have a grid. Think of this as maybe Midtown Manhattan. Think of this as like a big square. Imagine you have square streets. And imagine somebody randomly goes for each street and says, we're going to toss a coin, and if it's heads, we're going to shut down this street to traffic. We're going to make it open for pedestrians, put some nice plants there. We'll make it nice and lovely. And then the question is, once they do this randomly, is it still possible to drive from one river to another? Can you actually cross Manhattan after all of these things have done? Or you could say, imagine that you have a small child who is only allowed to cross streets where cars are not allowed. Can that child get from lower Manhattan up to upper Manhattan? And the idea is that, well, so each of these dark lines would represent a street that's open to cars. And each of these dotted lines will connect the center of one block to the center of another block, and that will represent kind of a pair of blocks where the child can get from one block to the other. And then the statement is that either, with probability 1, either there is a path for cars to get from the East River to the West River, or there is a path for the child to get from north to south. And there's never both. Okay, and then that tells you that the probability has to be 50-50, because it's always one of the two that happens. Okay, amazing implication of just this 1 + 1 = 2. Here's something called the Ising model, where you choose a random color for every point, but you sort of use a weighting that makes things that are close to each other more likely to be the same color. And this is kind of a model of magnetism, where spins in a magnet want to be aligned with each other if they're nearby. And if you kind of tune it to just the right parameters, you get this very nice picture where you get some black regions and some white regions, and it's all kind of mixed together in this beautiful thing. And various mathematicians and people in physics as well have spent the last few decades really understanding this model extremely well. Often in statistical physics, you want to find the very simplest models you can that nonetheless contain features from reality. And instead of trying to model everything in a real-world magnet, all of the particle physics going on with the neutrons and electrons and quarks and everything, you just say, let's take a very simple caricature of the thing where you just have a lattice thing. They're all just plus or minus spin. Let's understand that. And if it predicts behavior that agrees with our models, we can take other things about the model and use that to generate further predictions that we can test. So it's kind of a different way of thinking about physics. You take the very simplest caricature, understand that to death, and then use that to get ideas about what's going on in a sophisticated system. And that's what was done here. Here's a story where they colored the hexagons one of two colors, and they made one boundary all blue, one boundary all yellow. And if you look at it, there's a path that's an interface between these two, kind of a boundary between the yellow and blue that kind of starts down here and up here. And mathematicians have worked on understanding behavior of this path. All right, what else do we get from 1 + 1 = 2? Let's take this out for a spin. So first of all, Dirichlet energy. How many of you have heard of Dirichlet energy of a function? Okay, again, maybe probably the same 20% has heard of Hex. A few of you have heard of it. It's basically a measure of how much a function, how variable a function is, how much it's going up and down. And so imagine a function f from a planar domain D to the real numbers. And basically, I take what's called the L2 norm of the gradient of the function. So it's an integral of the square of the gradient of a function. So at any point, the gradient is sort of a measure of how steep the function is at that point. And you take the square of the steepness, and you integrate that over the whole space, and that's a measure of how much this thing's fluctuating up and down. So if f is a constant function, the Dirichlet energy is 0. If f waves up and down a lot, the Dirichlet energy is very high. So now let's consider a rescaled version of f. So write g of x is f of x over c. And so now g is a function from a rescaled version of d. So I sort of stretch the domain by a factor of d, and then kind of stretch out the graph of the function by the same factor. And you'll notice something. The gradient of g, like the steepness of this stretched out function, is smaller by a factor of d. I've sort of stretched everything out, but I haven't adjusted the height. I've just stretched the horizontal things, and so everything becomes less steep by a factor of c. So the square of the gradient is going to be smaller by a factor of c squared. Okay, but now what happens to the area when I stretch by a factor of c? Well, if you think about it, I stretch by c in one direction. That multiplies the area by c to the 1 power. I stretch by c in this direction. That also multiplies by c to the 1 power. When I do both of those, c to the 1 plus c to the 1 times c to the 1 is c to the 1 plus 1, which is c to the 2. Okay? So 1 plus 1 is 2. Tells me that these two effects exactly cancel each other out. The Dirichlet energy of F equals the Dirichlet energy of G. In other words, the Dirichlet energy is invariant under rescaling of the domain. So if I ask you, how wavy is a surface by this measure, and then I stretch out the domain, the new stretched out surface is assigned the same amount of waviness. It's considered to be the same amount wavy as the original one. That's an interesting fact, and that would not be true in any other dimension than 2. It's a very special effect that comes from this 1 plus 1 equals 2. Now, you can also extend this even further. If I take a function phi that looks locally like a rotation, translation, or scaling, so this is also invariant under like rotations and translations, then I'm going to call that function conformal. There's a special kind of function from the plane to the plane that if you look at a very small region, a very small circle here, it'll just get mapped to a small circle over here, and the circle might get stretched by some constant factor and rotated. But it kind of does that everywhere. And we call those functions conformal or analytic or holomorphic. There are various words for them, but they're very special functions. And it turns out if I write h equal to f composed with one of these conformal maps, then basically the same argument up here shows that the Dirichlet energy of this conformally trans function is the same as the Dirichlet energy function of f. Okay? So this simple fact about stretching out the domain means I could also do something a little bit weirder to the domain, apply one of these special conformal maps, and that would also preserve the Dirichlet energy. All right. You can use this to prove other things. We've started with 1 plus 1 equals 2. We got this. We can take a stepping stone and prove something else about 2 dimensions. So a function that minimizes the Dirichlet energy, given its boundary conditions, is called harmonic. That's another. And the fact that Dirichlet energy is conformally invariant means that this harmonicity is conformally invariant. So if I give you a domain and fix some boundary values and take the harmonic function with those boundary values, if I apply a conformal map, it will also have the same values. And it turns out that exit probabilities for a random path called 2D Brownian motion are governed by harmonic functions. So if I have a domain and I put a boundary conditions 1 on one arc and 0 on the other arc, and I look at a point in the middle, the harmonic extension to that point in the middle is going to be the probability that a Brownian motion started at that point hits the arc where things are 1. Okay, if you don't know what that means, don't worry about it, but it's just understand that there's something special about harmonic functions that tells you how Brownian motion behaves. And if you understand harmonic functions perfectly, you understand perfectly how Brownian motion behaves. And this in particular implies that Brownian motion is conformally invariant up to a time change. So here's what I mean. So let's say I take a point in the center of a box and do this two-dimensional Brownian motion. This is this actual, Brown, the botanist, looked under a microscope and saw that things like naturally randomly move around. And later Einstein and then others, Norbert Wiener, various people turned this into mathematics and gave kind of a very nice description of what these things are doing. And so here's a trace of where this particle went before it eventually exited the box. If I apply one of these conformal maps that maps the box to the circle and takes the center to the center, the image of this path here will be a new path over here. And the idea is that the image of this path here looks just like a Brownian motion in this new domain. So I cannot tell whether I ran the Brownian motion here and mapped it over, or whether I just started with a Brownian motion over here. That's a very special symmetry. And this was used to prove, for example, the outer boundary of this path, of the region traced by this path, is a random curve that Mandelbrot guessed way back in the 80s would have Hausdorff dimension 4/3. he kind of had an argument, but kind of very weird heuristic, not a very persuasive argument, but he kind of guessed the uncertain dimension is going to be 4/3. And people looked at the argument and didn't think there was much to it. But then some 20 years later, this is part of the Fields Medal for Wendell and Werner. He, along with Greg Lawler and Oded Schramm, were able to prove that, in fact, it actually is 4/3, the Hausdorff dimension of this boundary, and it's related to one of these special curves called Schramm-Loebner evolution curves. We call them now SLE curves. And they were to use these special conformal symmetries to actually really understand the boundary of this, as well as some of these other curves I've mentioned before. There's an object called the Gaussian free field, which is where you say take a random function f, where the probability density function of f is proportional to e to the minus the Dirichlet energy. Well, in probability, if I want to describe something like a Gaussian random variable, a normal distribution, I usually say, well, it's a random real number, and here's the probability density function. And it's usually like this bell-shaped curve or something like that. And the shape of the curve tells you properties of the function. But here, I'm not looking at the space of one-dimensional points. I'm looking at the space of functions and trying to do a probability measure on that. So I needed to assign a number to every function. And the number I assign is e to the minus his Dirichlet energy. And if I have a finite dimensional space of functions, that rigorously defines for me a nice probability measure. And I can restrict f to a finite dimensional space and make sense of that, take some limit as that space gets larger, and define f to be this limiting random generalized function. That's called the Gaussian free field. And the conformal invariance of this Dirichlet energy implies the conformal invariance of the Gaussian free field. So what do these random Gaussian free field functions look like? Well, I told you people started working on these. I, in particular, got involved in these in the early 2000s when this SLE theory came off. And here is an animated GIF that we first produced around, I don't know, what was maybe 2002 or something. A 24-year-old, so you can see that's kind of primitive technology. I guess it was possible to do better things back then, but this was, the right amount of memory that the computer could handle. And this is a time-varying version, but if you look at this thing at a fixed time, it'll look like this Gaussian field. It's a random function that it sort of wants to be flat. This you can think of it as a mesh of springs. So e to the minus energy is something that's big if the surface is flat. So it's it fluctuates, but then there's a force pulling it back to flatness, and over time, if you look at a fixed time, it's this Gaussian field. And you can do that on other domains with boundary conditions. And it's this whole theory that has this lovely conformal symmetry that's helped us understand this thing a lot better. Okay, uniform spanning tree, we can define a height function. So let me tell you what this is. So basically, if I give you any graph, let's say like a grid, a tree is going to be like a collection of edges in that grid where every vertex, basically it has no cycles, and it's connected. And a spanning tree will be sort of a maximal set of edges with this property. Every vertex is reached somehow, and there's only one connected component. And it turns out that correlations in the uniform spanning tree are closely related to those of the Gaussian free field. So we can use these related things to prove similar conformal geometries for the Gaussian for these trees, but also is 1 + 1 = 2 helps us understand something called the height function of this Gaussian free field. So here's, or of this spanning tree. So here, these are just randomly colored, the edges, just to make it look pretty. But here you imagine that you take a random spanning tree and just pick the 2 corner points. There will be a unique path that connects one to the other. I connect that path, and I colored that in blue just to see what one of these long paths look like. Otherwise, it's kind of hard to see what the structure of this thing is. And so this beautiful random tree, but imagine I took another spanning tree, and I took a dual path going from this corner to this corner. I can ask, how often does it intersect this path? Or I could pick a point here and ask, how many times does that intersect? Or just a line from here to here. And you can see if I picked a point in the center, I looked at the path from this to the boundary. Another point in the dual thing, I looked at the path that are for this boundary. If I picked a point in the center, I looked at the path from this to the boundary. Another point in the dual thing, I looked at the path from this to the boundary. Another point in the dual thing, I looked at the path from this to the boundary. And you can see if I picked a point in the center, I looked at the path from this to the boundary. Another point in the dual thing, I looked at the path that are for this boundary. there's a question of how much they wind around each other. They go the way out. Like if I just take a vertical line here and I take this path, and I ask how many times it winds. That's sort of like a net amount of times I intersect this path left to right. And the fact that paths in 2D intersect makes it very natural to look at these intersection numbers and use it to define winding numbers and height functions and things like this. And so a lot of the theory, the fact that all these things are connected to Ising models and Gaussian fields and other things, it has to do really with this fact that one-dimensional paths intersect. It's a very special thing in 1 + 1 dimensions. Also, the fact that 1 + 1 = 2 implies that one forms are self-dual in 2 dimensions. In particular, gradient vector fields, aka curl vector fields, can be transformed into divergence-free vector fields by rotating all vectors 90 degrees. I don't know, how many of you guys knew this fact already? Okay, a few of you, not everyone, but it's something they will teach you in multivariable calculus. When you learn about these vector fields, if you take these in 2 dimensions, if you rotate all your fields 90 degrees, it transforms from a curl-free vector field, which can be a gradient of something, to a divergence-free field. A very special thing. Obviously, if you take one form-valued white noise, it can be orthogonally projected onto a curl-free and divergence-free components. One is related to the gradient of the Gaussian free field, and the other is dual to the gradient of an independent Gaussian free field. So there are these wonderful symmetries that come up in this case. All right. There have been at least 5 recent Fields medals in probability. They have done mathematical physics results, often in dimension 2, some of them in higher dimensions. People have been very excited about these results. All of these models, Percolation, Ising, uniform spanning tree, that are intimately related to each other, they're all closely related to the Gaussian free field. There's scaling limits of paths, like level lines of the free field, branches of the uniform spanning trees, this interface between percolation interfaces, these Ising model boundaries. They turn out they're all related to these random fractal curves called the Schramm-Loeffler evolutions. And there's a whole branch of mathematical physics called conformal theory, field theory, for the last few decades that has really explored and expanded upon this area. In some cases, we can rigorously construct off-critical scaling limits that look like the models above at small scales but differ at large scales. Off-critical percolation, off-critical Ising, and so forth. And it turns out that the construction of one of these off-critical models in 4 dimensions, in the context of Yang-Mills gauge theory, is something that is this particular $1 million prize problem, this famous problem that is very unsolved. But okay, before we get into that, let's think about 2 + 2 = 4. I'm halfway through the talk, almost exactly now. It's time we switch gears. So I think we've covered 1 +. Anyone have any questions about 1 + 1 = 2? Is that clear? Okay, all right, good. So now 2 + 2 = 4. So 2 moving generic planes in 4D meet at a single point. Or sorry, 2 generic planes, not fully non-parallel planes in 4D meet at a point. And it's hard for you to visualize a 2-dimensional plane in 4 dimensions, unless you're a certain type of mathematician. Most have it a little hard to visualize. But one way you can visualize a plane in 4 dimensions is it is a line in 3 dimensions that moves in time. So if you think of 4 dimensions as space-time, a line that sort of moves at constant speed in time, that traces out a plane in space-time. Okay? And the fact that the 2 planes cross is basically the reason why if you have 2 lightsabers in a Star Wars movie and they are come to each other, there has to be a time where they would intersect each other. And depending on the type of lightsaber, maybe they could pass through each other and continue on. I don't know, but there has to be this some time where they intersect. Okay? So whenever you hear someone say that 2 two-dimensional planes intersect in 4 dimensions, you should always imagine 2 lightsabers coming at, and having a 4th dimension be time. 2 lightsabers moving in space-time and having be the special point where they intersect. There also, we can extend this, just like we did with mean value and Jordan curve theorem, to curve things. The fact that 2 loops cannot be disentangled without crossing each other is sort of a related result. to this thing that I told you about 2 points not being able to pass each other. 2 cars can't get past each other in 1 dimension. Well, here in 3 dimensions, 2 loops can't get past each other. And that's very closely related to this 2 plus 2 equals 4, the fact that 2-dimensional planes have to intersect. So basically, all of knot theory is a branch of mathematics that exists because 2 plus 2 equals 4. Also something called the Laplacian inner product. If I integrate the Laplacian of f dot the Laplacian g, that's scale invariant. And that tells you that a different random field, where instead of weighting by the L trinom or the gradient, you somehow weight by the L trinom or the Laplacian, this is going to be scale invariant and log correlated, in 4 dimensions. And it turns out that this special Gaussian field in 4 dimensions is very closely related to the special field in 2 dimensions, in the sense that if you restrict this 4-dimensional field to a 2-dimensional plane, you get that object I described for you in 2 dimensions. So it's a very closely related subject. There are also analogs of this hex crossing theorem, where lines are replaced by surfaces and 2D by 4D. Okay, sorry, this is the part that's going to kind of blow your mind a little bit if you haven't seen it before, but imagine that you have S is a square, and I write it as 0, 1 squared. So 0, 1 cross 0, 1. That's just a 2-dimensional square. Now, I let D be the square squared. So that's going to be the same as the interval to the 4th power. That's a 4-dimensional hypercube. So x, y, z, w, they're all between 0 and 1. If you think of this in time, a hypercube comes into existence at time 0, a regular cube, and then it disappears at time 1. That's this object. I want to decompose the boundary of this thing into 2 pieces. I take the square, cross the boundary of the square, and boundary of the square cross the square. It's a little hard to visualize, but the 4-dimensional cube has 8 faces, because I can set each of the 4 coordinates to be 1 or 0. And that would each of those things would correspond to 2 faces. 4 coordinates I can do that for. That gives me 8 faces. And this is going to be 4 of the faces linked together to make kind of a donut. And this is going to be other 4 of them linked together. Now, the overall boundary of this thing is 3-dimensional. So here I'm sort of linking together, I'm sort of taking these 4 faces, which each is a 3-dimensional cube, and I'm gluing them, 4 of them together in a way where they loop around and sort of form a donut with the inside filled. And then here, this is going to be a complementary donut. And I glue the boundaries of these donuts together in a weird way, such a way that one donut sort of goes through the other. And then I glue the rest of the boundaries together in a way so I identify all the other components of the boundary in a way that it becomes topologically a 3-sphere, which is the boundary of this 4-dimensional ball. It's a little hard to visualize. I don't know if you can quite see this. But basically, it's 2 donuts intertwined, and then the entire boundary is glued together, and it magically gives you the boundary of a 3-sphere. So I do what we call Heergaard splitting if you're a topologist. And what do I want to say? In some settings, what you can show is that either you have a surface that spans one of the donuts, which means it has a boundary of this surface. The surface might have handles, but it's some topological surface that has just one boundary component that goes around one of the donuts. Or you have a dual surface whose boundary goes around this complementary donut. And that at least one of those 2 things must happen. And this tells you in particular that if you have a model with some symmetry, each of those things has probability 1/2. So, okay, so what are the settings where this happens? So basically, if instead of tossing a coin for every edge to color it one color or another, you pick a square and you toss a coin for every square in your 4-dimensional lattice and color that one color, or don't color it, call that open or closed. Then the boundaries of this will have this property. It's a little hard to visualize, but it's kind of a nice toy. But it's sort of related to, you can think about it this way. Take this boundary of your box and then of this four-dimensional box, and gradually shrink that. And as you shrink the boundary of the box, think of of a time as telling you how far you've shrunk. Like time is the r in your polar coordinates, or a square version of that. So time is telling you how far I've shrunk this thing down. What I'm going to get is a movie. A surface is going to be a movie where these curves are moving in time. And the fact that these two loops cannot get past each other, or I can't close one up without cutting the other loop, is the reason why I can't have both of these surfaces existing simultaneously in this thing. So hopefully you get some sense of what's going on there. There's also a version called a four-dimensional version of a spanning tree, just like a two-dimensional spanning tree, which is also very closely related to Gaussian fields, discrete Laplacian determinants, has a lot of very beautiful properties. And that's where instead of picking a random collection of edges on a graph and saying you want no cycles, you pick a random collection of plaquettes in 4 dimensions, and you insist that you don't want it to make any two-dimensional closed surfaces that are orientable. Does that make sense? Put in a bunch of squares and try not to make a surface that's closed. It's a closed surface, like something that's topologically a sphere or a torus. You don't want to make that. And you want sort of a maximal thing without making that. And I wanted to try to draw a picture of that for you. And it was very hard for me to figure out how to do this. But here's what I was thinking. So if I wanted to show you a picture of a spanning tree, one way I could do it is I take this grid and I put in my nice tree here, and I make one of the dimensions time. So let's say time is going to move from right to here, and at any time I'm going to tell you what the tree looks like at that time. So at this time, when I'm at this point here, what you're going to see is some collection of edges. This edge is there, this one's not, this is not, some collection of edges. But at this time here, when I draw this here, what you're going to see is a collection of vertices. So you'll see some collection of edges, collection of vertices, edges, vertices, edges, vertices. So in 4 dimensions, I'm going to show you a movie where as you go through, you're going to see a collection of plaquettes, and then a collection of edges. And when you see the edge, you should think of it as that's an edge cross a unit of time, which means it's actually a plaquette that uses the time variable. So you'll see edges, these plaquettes that use the time variable. Then you'll see plaquettes that live in the XYZ plane, other plaquettes that use the time variable, and it'll sort of alternate between those. And all right, and I made these plaquettes a little bit transparent so you can kind of see the whole thing. I don't know. Let's just see if this says anything to you. By the way, the blue one is the actual thing, and the red one is the complement. So you can see this is the tree, and these are the plaquettes whose duals would be in the dual tree, because there's this duality between these trees and the dual trees in 4 dimensions. So I don't know. Does this say anything to you at all? I don't know. It's just a bunch of plaquettes. Well, what you can see here is if I were to add one extra plaquette anywhere in this system, there would be a closed surface that had that plaquette as its boundary. So just like in 2 dimensions, I could pick 2 points, and there's a path. Here, I can pick any square or even any surface, and there will be some spanning surface that has that as its boundary, which would be the analog of a branch of the tree. And it won't always be integer valued. It can be kind of a complicated thing sometimes, but it's there's a nice analogous theory. Okay. And really, another way to think about this is just to think about what happens in 3 dimensions. So 3 dimensions, if I give you a random collection of plaquettes, and I tell you that adding one more would make a surface, that's actually, every plaquette is dual to an edge. If I give you a 2 by 2 square, there will be sort of an edge that starts in the center of a cube, goes to the center of a cube above it, and that passes through the plaquette. So there's a certain duality between ordinary spanning trees, and these plaquette spanning trees are just their boundaries. The reason for that is that 1 plus 2 equals 3. So these plaquette theory and this edge theory are naturally dual to each other in 3 dimensions. And so if I just take a uniform spanning tree, root it at the bottom and top of this thing, and then look at the part of the tree that's rooted at the bottom, the boundary of this is going to be some surface. This is one way of making a random surface in 3 dimensions. It's a bunch of squares that glue together. So this you can maybe visualize more easily than what I just showed you in 4 dimensions. It looks more like a surface. Here's another one on a larger grid. You can see sometimes you get holes, things like this. So critical percolation. Here, I could look at, a large cluster that's connected to the boundary. If I put all the boundary, you get some very nice patterns like this. Okay, now finally we get to Euclidean Yang-Mills gauge theory. This is the last 10 minutes of the talk. Well, I promised I would connect this into this famous $1 million problem. Well, okay, what do we want to do here? So basically you have a graph. The picture here is 2 dimensions, but eventually you want it to be in 4 dimensions. And every edge, you assign a random matrix to that edge. And so here I have these random matrices, one for every edge. And the rule is that if I reverse the direction of the grid, I replace the edge with its inverse, with the inverse matrix. Okay, so there's a certain symmetry I'm imposing on this thing. So it's sort of like a flow on the edges. I reverse the edge, I get a reverse matrix, a matrix-valued flow. And what I want to do is choose this randomly. So what I do is I choose first the matrix from one of these natural groups of matrices. So it turns out like a 3x3 matrix encodes like the set of ways of rotating a 3-dimensional object, the group of orthogonal matrices. Oh yes, let me move this down again. Sorry, yes. So I can look at this. This would be like, a group of the things I can do. That's called a Lie group. It's just a continuous way of moving things around. It's encoded by a certain set of matrices. And there's a natural way, it's something called Haar measure, which is a random way of choosing an element of this group. But I can put a weight on that Haar measure that weights, so that the product of the matrices around any plaquette, so the matrix for this directed edge times the one for this directed edge times the one for this directed edge, which is the inverse of this, times the one for this directed edge. I want the product of all those matrices to be close to the identity. And how do I do that? Well, I put the density function is going to be a function that is big when you're close to the identity and small when you're not close to the identity. Anyone know a natural real valued function that's big when you're close to the identity and small when you're not? So the one I like is called the trace. I know you've heard of the trace of a matrix. Just like the sum of the diagonal elements of the matrix. So it's basically, it turns out that all of the eigenvalues for these kinds of matrices are points on the complex unit circle. So they're complex. So they're, if you know what eigenvalues are. If you don't know, don't worry. But it's just a particular property of the matrices. And if you take the real parts of them, are always between -1 and 1. And when they're all close to 1, the matrix has to be close to the identity. This is a particular way that makes these things want to be close to the identity. And so I can weight by, for example, the exponential of beta times the sum of the real parts of the plaquette traces for all these plaquettes. And now I can ask questions like, if I take a large loop, what's the expected product of the matrices around all of the product of the matrices around that large loop? Okay, and so there's something that physicists call quark confinement, and mathematicians call the area law, which says that as this box gets bigger, the expected trace for a large loop gets smaller, which sort of makes sense when you take a product of a whole bunch of matrices. A lot of randomness, things get all mixed up. So negative and positive are equally likely. It's centered near 0. So average that to be 0. But the expectation decays exponentially in the area of the loop. And so that somehow is related to the fact that quarks are hard to pull apart. Don't ask me to explain all the physics, but just the mathematical statement is just this exponential decay of correlations in the area. So it's like e to the minus some constant times the area of this curve. And this other thing says that if you take 2 small loops and you take them farther apart, you should have an exponential decay in the correlations They become more and more independent and unrelated as they get further apart at an exponential rate. And that is something related to what physicists call mass gap. It's like probably the reason certain particles have mass, some gap between the eigenvalues in some quantum field theory. You don't have to worry about all the physics for now, but it's just some property of the system that is important in physics. And the problem that you would get the $1 million for winning is to, or you would win the $1 million for solving, is to construct and understand the basics of a continuum version of this model. So ask what happens in this model as this mesh gets finer, there should be some sort of a limiting model, just like I have a percolation. You take finer and finer grids, and some properties, like do you have a crossing here to here, they're still interesting for some sort of a continuum limiting model. You want to figure out what natural properties are still interesting in the limit for this model. Take a limit in such a way that you can describe those properties in the limit, get some nice limiting theory that you can understand, prove some basic axioms about this theory. That's what you get $1 million for doing. It's not the easiest way to get $1 million, I don't think, especially not in this town. Probably there are other ways, far, far cheaper ways, easier ways to win that much money. But that's, became a very famous, that's partly famous for that reason. Physics is famous for other reasons that, it's a very core to the standard model of particle physics. So lattice Yang-Mills, we assign this random matrix. Okay, so I already said all this. So this is like the Ising model. So in the Ising model, you have a random 1-by-1 matrix for every vertex. This is from the orthogonal group of 1-by-1 matrices, meaning it's just a 1 or a -1. So all your matrices are 1-by-1. And the weight is for every edge, you say you want the product of the two matrices on the boundary of that edge to be close to 1. So you think of these as spins, you're sort of biasing it so that spins want to be aligned when they're next to each other. Okay? So you're using edges to do your weights, and you're using 1-by-1 matrices. This gauge theory model is exactly the same, except that you go one form level higher. So you replace edges with plaquettes. So instead of your matrices living on vertices, your matrices live on edges. And instead of wanting the matrices along an edge to be compatible, you want the matrices along a plaquette to be compatible. But in both cases, compatible means the product is close to the identity. Here it means -1 times 1. It's close to the identity, meaning it wants to be 1. It wants to be the identity. And here it means you want to be. By the way, this particular group of matrices in the picture is the group of 90-degree rotations and reflections of the plane. They're just easy to draw because they're all 1s and 0s. If these were samples from an orthogonal group of matrices, it would be sort of like random real numbers, and I could show them to 9 decimal places, but it would be a much messier picture. All right. So that's the problem. And it turns out that these Yang-Mills models are very closely related to random surfaces. So you can, there are a lot of statistical physics models where you get collections of loops. So this is going back to 1 + 1 = 2 world. And if I want to know something like the correlation between what happens at x and y, what I really want to do is ask, how expensive is it if I want to put a defect here, and force there to be a single open path here instead of a bunch of loops. So there's like a certain what they call a partition function, like the total amount of randomness in this model, a revised partition function for this model, and I ask, how different is this model? How much do these x and y affect these things? How much energy is there I have to insert into the system in order to insert these points? So there's a way of making sense of all of that in 2 dimensions. And and there's some models where as you move x and y apart, the price you pay is exponential in the distance, and some where it's like polynomial in the distance. And it turns out that in there are also models of random surfaces, random 2 forms, where you can ask, what's the, I have this random collection of closed surfaces, and that's what's the price of saying I want to insert one long loop like this. And then there has to be a surface spanning that loop. And there are some models where the price is exponential in the area spanned by the loop. And somewhere it's more like exponential in the perimeter of the loop. So the cost doesn't care about the interior of the loop as much. And basically, a big part of this quark confinement problem is showing that in the random surface models that are related to Yang-Mills theory, that you get something of this type where the price is exponential in the area. So, in short, we have a way, and these are a few papers we've done recently on this. Probably there are many more. These are just some of the ones I was involved in recently. Basically, there's a lot of work. Some of it is very old. Some of this has been known for almost 50 years, and some of it's very new, very recent. But there are a lot of different ways of taking these Yang-Mills models and expressing these Wilson loop expectations, these fundamental quantities, observable quantities, as sums over random surfaces, where basically you're asking what's the insertion cost of this big loop in some natural statistical physical model. And then the question is, how much can we use the miraculous properties of 2 + 2 = 4 to understand the way these surfaces interact with each other in 4 dimensions? And I would tell you how to solve the problem, but it looks like I just ran out of time. So I think I'll stop there.
Time for some questions. Yeah, why don't we start or in the red, maroon?
Yes.
How much is known about these lattice models in dimensions higher than 4, like in 6-dimension conformal field theory or something?
6 dimensions or higher? So, there's some things you can do in any dimension. So there is this beta parameter I mentioned that tells you sort of how strongly you weight things to want to be close to the identity. And if you have this system where you don't weight it strongly, that's what we call high temperature. It's known that sort of in any dimension, when you get to a high enough temperature, you're going to have this kind of area law, at least for any group where you have a center. And so there's some properties like this that really work for any dimension. There are other things that are believed to be special to dimension 4. So like if you just do like U1 gauge theory, where you have just a random point on it, it's a 1-by-1 matrix, but a complex valued, and so it can be any point on the unit circle, a complex number on the unit circle. So when you do this theory, it's sort of understood that in 3 dimensions and lower, you will somehow, I guess, always have this area law, always have exponentially k of correlation in area law. And in 5 dimensions and higher, you never will. And then, I guess 4 dimensions and higher, you have a phase transition. So like in 4 dimensions, there's this special transition, some beta where you suddenly change from being area law to not area law. And then in 4 dimensions, it's supposed to be that when you go to any other group, like non-abelian Lie group, that suddenly you're always area law at that range, even at very high temperature. So what makes 4 dimensions special is that it's where you really expect different behavior at large beta, depending on whether the group is abelian or not. And so that really matters at large beta. And there are a ton of variants of what I've just talked about. You can put in Higgs mechanisms, you can put in bosons or fermions, you can put in mass fields, matter fields. There, I think we looked at one point, if you look at like gauge theory problems in physics. There are like maybe over 1 million papers written on lattice gauge theory. So really, it's impossible for anyone, let alone a mathematician like me, to keep track of everything that's going on in the physics world. And a lot of the things they do higher dimensional things. Apparently there are, I've been told that there are cool things in 6 dimensions. Someone told me the other day that 3 + 3 = 6 is actually important for some. There are some physical theories that take advantage of that. There's some 6-dimensional string theory or something, but don't quote me on that. I hope this isn't recorded. No, I'm kidding. It is recorded, but I think it's okay. I'm not saying anything too scandalous, I don't think. But I'm told there are some cool things in 6 dimensions, but I don't know that much about them. So you might have to ask some other sources. Yes, go ahead.
Okay, so I understand 1 + 1 = 2 and 2 + 2 = 4. I want to know, how would you differentiate between 2 + 2 = 4 and 2 × 2 = 4?
2 + 2 = 4 and 2 × 2 = 4. Yeah, I haven't been too careful about differentiating between those two things. There's some places in this talk where I claimed it was 1 + 1 = 2, where it might have been that 1 × 2 = 2 would also have done the job. Like when I was stretching by C in this direction and C in this direction. Yeah, I don't know. I don't have anything too wise to add to that question, I guess, at this point. Yeah, go ahead. So.
You mentioned that if you restrict the 4D object to a 2D plane, you get the same conformal invariance as with all the 2D objects we saw. But is that like a slice or a projection, which might relate to the previous question?
So it's a slice. Oh. It's a 2-dimensional slice. So it turns out these Gaussian random fields I'm describing, they're not actually random functions. They're generalized functions. So they're not actually defined point-wise, but if you multiply by a smooth function and integrate, you get something well-defined. So if you haven't heard of that before, just think there's this weird notion of function that they use in physics, where they're sort of too rough to be well-defined as actual functions. In some cases, you can actually restrict one of these functions to a plane and make sense of that. Maybe you restrict it to a strip and then take a limit as that thing shrinks to 0. There are ways of doing this. Not always do you get something meaningful this way, but sometimes you do. And this is one of the examples where you do. And this thing, when you restrict to this 2-dimensional plane, it literally is this 2-dimensional Gaussian free field. And so it has log correlations, where these other natural Gaussian fields will have polynomial correlations. So there's a whole theory. If you look at this paper here, Fractional Gaussian Forms and Gauge Theory, we really kind of go into depth in studying just the Gaussian versions. And so all of these gauge theories, depending on how you tune the parameters, there'll be some limits of them that are just Gaussians. It'll be some Lie algebra valued Gaussian free field on 1 forms. If you don't know what all that means, don't worry about it, but it's a random generalized function that at least to mathematicians and physicists would seem very simple. And then, physicists often use the word trivial. They say, okay, it's the trivial field. It's just Gaussian. It almost doesn't count as doing conformal field, quantum field theory. You just got this boring Gaussian one. And the hard part is constructing the non-Gaussian ones, being able to perturb behavior to get something that looks Gaussian at small scales, but is interesting and non-Gaussian at large scales. And so this, the Yang-Mills theory that they're all after, that would be the prize-winning object, is going to be an object that will look just like this Gaussian field at small scales, and at large scales it looks different. And and so I'm part of a Simons collaboration. Also funded by the Simons, we have a grant where the Simons Foundation is funding us to work on these problems together. And I have a number of colleagues who are working on different aspects of this. But one of the approaches is to say, kind of start with this Gaussian field, and then just try to perturb it in time. This is what Martin Heyer and co-authors are doing, others are doing, and try to show that over time, you have a dynamic object that in time will converge to sort of one of these non-Gaussian theories. But a lot of these constructions use the Gaussian thing as a starting point. Then you just want to try to nudge just a little bit off of that and get something else interesting. Yes, go ahead.
Two questions regarding dimension. I mean, I would imagine that if the dimension is high enough, sort of naively, mean field theory should be exact, no? Because you have enough neighbors that sort of fluctuations are suppressed. Then usually what happens, right, in high enough dimension, mean field theory works. And then the related question, I mean, in 2 dimensions, for example, you can solve the Ising model exactly.
Yes.
Can you do the same for Young mills in 2 dimensions?
Yes, okay. So the first part of your question, I think it was more of a statement. You're telling us that in high dimensions, a lot of times these models become simpler.
Yeah.
And you know, things become more like trees or more like complete graphs, and things become solvable. And I agree with that. And the second thing you were asking about is what's 2-dimensional Yang mills? Is that easy to solve? Well, it turns out there's a weird symmetry where if you look at all the matrices directed into an edge, you can multiply all those matrices on the right by the same matrix. So if this is A, B, C, D matrices coming in here, and I say A times E, B times E, C times E, D times E, doing that variant, it doesn't actually change the product around any loop. So it's what we call a gauge symmetry of the model. And using these gauge symmetries, you can somehow reduce the model to one in which certain edges are just the identity. In fact, you can take any spanning tree of the model and fix all the edges on that to be the identity. Well, if you're doing this in a 2-dimensional grid, I could say take all of these edges, do a spiral like this, and take all these edges to be the identity. And then these edges here are the only ones that are not, where there's some randomness. And the price I pay for the plaquettes, a plaquette will be like, go here, it can include at most 2 of these green edges. And it basically says this edge times sort of the opposite direction of this edge should be close to the identity, which just means these 2 matrices are going to be close to each other. And so it sort of just says, I get kind of a 1-dimensional chain of matrices where any 2 matrices in the chain want to be close to each other. So it sort of reduces to a 1-dimensional Markovian model, if you know what that means, which starts to look more like what we would call a Brownian motion on the Lie group, if you know what that means. And so if you don't, just the upshot is somehow a lot of things become a whole lot simpler in 2-dimensional gauge theory, to the point that physicists will say this is basically trivial. You know, we can understand, you can find some non-trivial questions to ask in 2D gauge theory. In fact, I think one of these papers up here is about 2D gauge theory. Maybe this one here. No, you know, we've tried to, there are some interesting things you can say, but somehow the starting point is just Brownian motion on Lie groups. And that's interesting, but the problem of rigorously defining the continuum limit is not the big puzzle that it is in 3, 4, and higher dimensions. It's something that we just know how to do in 2 dimensions. And the problem is figuring out how to do that in higher dimensions. What's that?
Time for questions we have right now. Scott will stick around for a sec.
Okay, I'm happy to talk more if people want to come up.